Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 5, Conic Sections. Section 42, Tangents, Points of Contact. Definition: a line P in the plane of a point conic which meets the point conic in one and only one point P is called a tangent to the point conic at P. A point P in the plane of a line conic through which passes one and only one line P of the line conic is called a point of contact of the line conic on P. Theorem 5. Through any point of a point conic, there is one and only one tangent to the point conic. Proof: if P0 is the given point of the point conic and P1 is any other point of the point conic, while P is a variable point of this conic, we have, by Theorem 2, P0 pencil P is projective with P1 and pencil P. Any line through P0 meets its homologous line of the pencil on P1 in a point distinct from P0, except when its homologous line is P1, P0. Since a projectivity is a one-to-one correspondence, there is only one line on P0 which has P1, P0 as its homologous line. Theorem 5'. On any line of a line conic, there is one and only one point of contact of the line conic. This is the plain dual of the preceding theorem. Exercise: give the space duals of the preceding definitions and theorems. Returning now to the construction in the preceding section for the points of a point conic containing 5 given points, we recall that the point of intersection C1 of a line L through B2 was determined by the quadrangular set Q with point triple B2ST and triangle triple C1AU. The points B2 and C1 can, by the preceding theorem, coincide on one and only one of the lines through B2. For this particular line L, A becomes the intersection of the tangent at B2 with B1C2, and the collinearity of the points A, B, C may be stated as follows. Footnote: as explained in the fine print on page 110, this occurs when L passes through the point of intersection of B1C2 with the line joining C equal to A1B2, A2B1, and B equal to A1C2, A2B2. Theorem 6. If the vertices of a simple plane 5-point are points of a point conic, the tangent to the point conic at one of the vertices meets the opposite side in a point collinear with the points of intersection of the other two pairs of non-adjacent sides. This theorem, by its derivation, is a degenerate case of Pascal's theorem. It may also be regarded as a degenerate case in its statement if the tangent be thought of as taking the place of one side of the simple hexagon. It should be clearly understood that the theorem has been obtained by specializing the figure of Theorem 3, and not by a continuity argument. The latter would be clearly impossible, since our assumptions do not require the conic to contain more than a finite number of points. Theorem 6 may be applied to the construction of a tangent to a point conic at any one of 5 given points P1, P2, P3, P4, P5 of the point conic, figure 53. By this theorem, the tangent P1 at P1 must be such that the points P1, P3, P4 equals A, P1, P2, P4, P5 equal B, and P2, P3, P5, P1 equal C are collinear. But B and C are determined by P1, P2, P3, P4, P5, and hence P1 is the line joining P1 to the intersection of the lines BC and P3, P4. In like manner, if P1, P2, P3, P4, and P1 are given, to construct the point P5 on any line L through P4 of a point conic containing P1, P2, P3, P4, and of which P1 is the tangent at P1, we need only determine the points A equal to P1, P3, P4, B equal to L, P1, P2, and C equal AB P2 P3. Then P1C meets L in P5, figure 53. In case L is the tangent P4 at P4, P5 coincides with P4, and the following points are collinear, figure 54. A equal to P1, P3, P4, B equal to P4, P1, P2, C equal to P1, P4, P2, P3. Hence we have the following theorem. Theorem 7. If the vertices P1, P2, P3, P4 of a simple quadrangle are points of a point conic, the tangent at P1 and the side P3, P4, the tangent at P4 and the side P1, P2, and the pair of sides P1, P4, and P2, P3 meet in 3 collinear points. If P1, P2, P3, P5, and the tangent P1 at P1 are given, the construction determined by Theorem 6 for a point P4 of the point conic on a line L through P3 is as follows. Figure 53. Determine C equal to P1, P5, P2, P3, A equal to P1L, and B equal to AC P1, P2. Then P5B meets L in P4. In case L is the tangent at P3, P4 coincides with P3, and we have the result that C is equal to P1, P5, P2, P3, A equal to P1, P3, B equal to P1, P2, P5, P3 are collinear points, which gives Theorem 8. If the vertices of a complete quadrangle are points of a point conic, the tangents at a pair of vertices meet in a point of the line joining the diagonal points of the quadrangle, which are not on the side joining the 2 vertices. Figure 55. The last 2 theorems lead to the construction of a point conic of which there are given 3 points and the tangents at 2 of them. Reverting to the notation of Theorem 7, figure 54, let the given points be P4, P1, P3, and the given tangents be P4, P1. Let L be any line through P3. If P2 is the other point in which L meets the point conic, the points A equal to P1, P3, P4, B equal to P4, P1, P2, and C equal to P2, P3, P4, P1 are collinear. Hence, if C is equal to L of P1, P4, and B equal to P4 AC, then P2 is the intersection of L with B, P1. In case L is the tangent P3 at P3, the points P2 and P3 coincide, and the points P1, P3, P4, P3, P1, P4, P4, P1, P3 are collinear. Hence, the 2 triangles P1, P3, P4, and P1, P3, P4 are perspective, and we obtain as a last specialization of Pascal's theorem, figure 56. Theorem 9, a triangle whose vertices are points of a point conic is perspective with the triangle formed by the tangents at these points, the tangent at any vertex being homologous with the side of the first triangle which does not contain this vertex. Corollary, if P1, P3, P4 are 3 points of a point conic, the lines P3, P1, P3, P4 are harmonic with the tangent at P3, and the line joining P3 to the intersection of the tangents at P1 and P4. Proof. This follows from the definition of a harmonic set of lines on considering the quadrilateral P1A, AB, BP4, P4, P1. Figure 56.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.